So yeah, just the last part of the overview at the beginning is going to be about chemical kinetics. Again, the general theory for chemical reactions. We'll look a bit about steady state approximations as well, and just collision theory. So very basics again. So for us to understand is the rate of a reaction is a function of the concentration of the species in the mixture, and the temperature and the pressure. So in our reacting flow simulation, of course, pressure will be determined by the initial conditions of the system, temperature as well, reactant concentrations, and then as the process proceeds, all of these things are changing. The concentrations are changing as the reactants are converted to intermediates. The temperature is changing depending on the exothermicity and the endothermicity. The pressure might change if the volume is confined. And all of these things we need to track at every time step in the reactant flow simulation, so we can predict again at the next time step what will be the updated species concentrations, temperatures, and pressures. So for a very simple reaction, again, A plus B goes to Q plus S. The reactants undergo the rate of reaction of species A is the change of number of moles of species A as a function of time. Similarly for B, it's change of number of moles as a function of time. Q, and note here the negative sign. So the rate of reaction for a reactant is always minus change of number of moles as a function of temperature. For species, it's plus change of number of moles with respect to time. Sorry, not temperature, with respect to time. And then we have a reaction progress variable. The reaction progress variable links all the different changes in species with each other. So the overall reaction progress variable for one reaction is a unique value, which is 1 over the stoichiometric coefficient for a reactant by the number, multiplied by the number of moles as it changes with time. And depending on the stoichiometry of the reaction, the progress variable determines how everything else is converted as well. So 1 over A for every, let's say, lowercase a of reactant A that reacts, then the stoichiometric proportion for reactant B has to react. Similarly, the products, their stoichiometry determines the overall rate of reaction and the change in number of moles of those species. Now, this is something we will use when we start doing simulation, if we were to write the code, because we can calculate the reaction progress variable, and if we know it for the change of number of moles in one species as a function of time, we can determine the change of everything else as a function at the same time, depending on the stoichiometry of the system. All the reactions are governed by the law of mass action. So that's where we say the molecularity of a single chemical reaction is based on the number of moles which must interact in the system. And for a unimolecular reaction, species A goes to products. The law of mass action says the rate of reaction is K, some rate constant, times temperature, or function of temperature, times the concentration of species. So this K, function of temperature term, is what gives us the temperature dependence of our system. Bimolecular reactions, if you have A plus A going to products, its rate of reaction is K times concentration of A squared. If it's A plus B, it's K times concentrations of A and B. And termomolecular reactions, same thing. You will multiply, if you have 3 reactant A molecules, you have to raise them to the power of 3, and so on. Now, most of the time in our elementary chemical reaction set, whenever we make a chemical kinetic model, it's a list of elementary chemical reactions. We typically only have unimolecular and bimolecular reactions. You will not find termomolecular reactions. Can anyone tell me what do we mean by when we say elementary chemical reaction? What is that unique? And tell us about it, the system. Yes? Okay. Well, it's single step, yes. but it can be pressure dependent. We'll come to the pressure dependence, that's possible. So you can have pressure dependence for an elementary reaction. But yeah, it will, when we say single step, yeah? 1 mole of each species. Well, you can have stoichiometry coefficient, which is not 1. But typically, there will be 1, but not necessary. So elementary reaction says it has to follow the law of mass action. That's for sure. So let's say if R reaction rate is R for A plus B goes to products, if the reaction is Kc times the concentration of A times the concentration of B, it would be definitely an elementary reaction has to follow that. Sometimes you come upon a reaction, and we'll talk about that in the next class. Kc, it becomes times A, concentration of A, times concentration of B raised to 1/2. That's possible. The order can be 1/2. So if the order of the reaction is not equal to the stoichiometric coefficient, in this case it's 1, but if it's raised to 1/2, it's definitely not an elementary reaction. So for elementary reaction, the order of the reaction, the reactants have to be raised to their stoichiometric coefficient. That has to be the case. It has to be single step. When we say single step, the true definition of elementary reaction means there's only one single transition state. Okay? So the reactants, A plus B or methane, well, methane plus oxygen is not an elementary reaction because methane plus oxygen going to CO2 and water does not proceed through a single transition state. Yeah? There's thousands of transition states that have to be created before for this reaction to happen. So, but in a chemical kinetic model, every reaction has to be elementary. So, as I said, this CH4 plus O2 going to CO2 plus water is not elementary. Even if this, and we will talk in the next class, if you were to conduct this reaction in a system and you were to measure the reaction rate R, you would find that it's not proportional to CH4 to the raised to 1 and O2 raised to 1. There'll be some weird exponent depending on the temperature or pressure of the system. So this is how people find out it's not elementary. So there must be some series of elementary reactions. One of them could be, yes? So O2, this is a radical, okay? So O2 could grab a hydrogen from CH4 and make a CH3 plus HO2. This would be an elementary reaction. How do you know? Well, I'm telling you it is. You would only know if you were to determine that this undergoes a unique transition state, yeah? And again, you can do that, you could calculate it, but people have calculated it many times. So this reaction could go through a single transition state, yeah? So like this, we'll have many different reactions in the mechanism, and we'll look at these later, like examples of reaction mechanisms, but keep this in mind. Chemical kinetic model should be a list of elementary reaction steps, and each step has kinetic parameters and, of course, thermodynamic data. For these species, you need the heat of formations, the entropies, you can get the equilibrium constants, and so on. And this would be a reversible reaction. And that's why you typically don't see thermomolecular reactions, because three molecules colliding together to make one transition state and products is almost impossible. Yeah? It's a very unlikely event. Therefore, you don't see any types of thermomolecular reactions in chemical kinetic models. Elementary reactions are either unimolecular or bimolecular in nature, because that's the only time you'll get a single transition state formed before you get to the products. Okay, then all these reactions, these elementary reactions have to follow will follow the temperature dependence described by the Arrhenius law. So again, we say reaction rate is a function of Kc times T, the Kc, not times T, Kc, which is a function of temperature, okay, and the concentration of species raised to their stoichiometric coefficients for an elementary reaction. And this Kc is a function of temperature. We call it the rate constant, but it's not constant because it changes with temperature and pressure. Yeah? And it's the way we express it in classical Arrhenius term is simply Kc is some pre-exponential factor times exponential minus an activation energy term divided by the gas constant R times the temperature. And you could say this exponential minus EA over RT is the Boltzmann factor, which describes the change in the potential energy of the system. Now, this is what we typically use, but when you guys start looking at kinetic models, we use sometimes a modified rate expression, which is like this. So this is simply a modified rate expression where we have 3 parameters to fit. Yeah, so this is now, we have a pre-exponential factor A, we have an N term or a beta, sometimes people say, and then you have the activation energy. Okay, that's just a modified rate expression. Most of the kinetic models today we use will have this form of the rate expression, like in Kempkin and Cantera. So you'll have an A and an N term, which many times is just 0, and then an activation energy term. So this activation energy, oh, by the way, let me just touch upon one other point here. Now, this Arrhenius rate expression, we should be mindful, it's simply a fitting expression, okay? This A term does not necessarily correspond to anything in physical sense. It can be related to the number of collisions that are probable to happen. The activation energy we see there is, we say it's a activation energy, which is the barrier for the reaction to happen. But again, it may not necessarily be the case. For example, in true sense, if we were to look at energy of species and reaction progress, what I've labeled it there, or coordinate, they say, okay, it's fine. This is more related, this is in a classical transition state theory, this is your reactants, this is your products, this is your transition state, okay? This is the change in energy from the reactants to the transition state, from the products to the transition state. You can have another activation energy here. So you can have 2 different activation energies, one for the forward reaction and the reverse reaction. Now, if I were to calculate from first principles this energy, I would determine the stationary point energy of the reactant, the energy of the transition state, and the difference would be this energy, difference in energy, activation energy. That energy may not be the same one you put in your rate expression, because the rate expression is simply a fitting of this K as a function of temperature, as we'll see in the next plot. We simply plot this rate, K, and as a function of 1 over T, and we take the slope of this line of ln K versus 1 over T, and the slope is the activation energy based on that standard Arrhenius rate equation format. And A is the place where it crosses the y-axis. So they're simply fitting parameters. If I bring in an n term here, T to the n, I've just brought in another fitting parameter. That might even change the activation energy, because I add another way of expressing K in a temperature dependence with N and with EA. So let's not, when you look at a reaction mechanism and you see these different activation energies, it doesn't necessarily mean this activation energy is the same as the barrier height for the chemical reaction. especially if you see an N term. N term is just a way of giving an additional curvature to these lines. Because sometimes if we do a calculation of the energy of a reaction at different temperatures, and then we were to fit K as a function of 1 over T, many times you don't get a straight line. You get something that's slightly curved. And we'll see that again later on. And whenever you have those curvatures, you can't plot it with a simple Arrhenius form. So you put an N term, and then you fit it that way. So these are all fitting parameters, not necessarily directly linked with the true energetics of the system. And that's something we should keep in mind, okay? Okay, then again, here, this is showing for a decomposition reaction. You know, activation energies are around 30 kilocalories per mole, but they'll change plus or minus 1 or 2 kcals per mole. Isomerizations are a bit slower. They have less temperature dependence compared to decomposition and so on. And we'll be looking at many different types of reactions over the next few days, and you'll see how they differ for different types of reaction classes. Okay, then the pre-exponential term is typically governed by collision theory, okay? So this is based on if two molecules were to collide, then they need to undergo proper orientation in order to react, okay? So for simple kinetic theory, it came from Bose-Einstein equations. Einstein said that if you have two molecules of suitable orientation, then their reaction will proceed. And you can say the collision theory, the collision rate is based on the concentrations of species multiplied by the hard sphere collision diameters. So sigma AB squared times 8 pi Boltzmann constant times temperature over the reduced mass of the species. Now this hard sphere collision diameter is assuming molecules are behaving like spheres. You can calculate the collision diameter of a molecule. Given sufficient temperature, high temperature, the collisions will be sufficient. And based on the concentration, you can get the overall collision rate. And then you can write again in this form, the rate constant, sigma AB squared times function of Boltzmann constant temperature and reduced mass. And then you could say then, from this ZAB term is some kind of pre-exponential, is related to collision theory. But again, not necessarily the case that this ZAB, this collision rate, is the same as a factor that you find in a model, because this is only if T has the exponential of 0.5, and many times it may not have this. And that's how we can then think of some modifications are not necessarily that ZAB is only related to this rate expression. There might be some steric factor, steric probability factor, which makes this pre-exponential term not necessarily the same as the one that's calculated from this collision theory. Now, why this all came important? Well, there was a guy, we said in the beginning, Hinshelwood. Hinshelwood was the first one to show that there are many reactions which are not following this collision theory. That's how this whole idea of reaction mechanisms, sequences of reactions, he found that, again, you take a reaction like CH4 plus O2, and if he were to measure the rate at different conditions, he found at some conditions he would measure the rate, and they did not agree with collision theory. The rates were different. Yeah. So again, an elementary reaction, a series of elementary reactions may or may not follow collision theory. If something does not follow collision theory, definitely it's not elementary. And that's how, and we'll talk in the next class, Hinschel would start to recognize some patterns in many different types of reactions which didn't follow the simple collision theory. And he said, okay, there must be something more complicated happening. And that means then you have a series of reactions which have different types of rate expressions, which then, as they all combine together, lead to manifest themselves in something that does not follow your standard collision theory for single reactions. Okay, we also can look at different types of reactions and how a series of reactions then might influence the outcome of a system. So let's look first at two reactions happening in series. So again, this CH4 plus O2 might be hundreds of reactions happening in series. Let's look at just what happens to a system if it's just two reactions in series. So reactant A undergoes some rate of conversion based on a rate constant, which is a function of temperature, to species B. And species B then is converted by a second reaction to species C. Now, if we were to put all of this inside of a box, we can write the simple balance equations as such. So for the isothermal system, fix the temperature, determine the rate of change of species. So change of A as a function of time is minus, because it's negative for the reactants, K1, the rate constant for the first reaction, times concentration of A. B is simply plus K1A, the rate of formation based on the consumption of A, and then the rate of decomposition based on the consumption in reaction 2, so minus K2B. And then product C is dC by dt is plus K2B. Simply it's wholly formed by reactant B. And if we have initial values at time equals 0, A equals A naught, concentration of B naught and C naught are 0. We can make a simple set of equations like this. A is A naught times exponential minus KT. Okay, similarly for B, concentration of B and concentration of C based on these equations here. And then we can plot how this might look. So A is 1 at the beginning, it's decreasing as a function of time, and again, time here is simply K1 times T, so some arbitrary time scale. It's decreasing. As it's decreasing, B is formed, but then as B is increasing, it has to also start being consumed to form C, so then species C is continuously formed. Now this is assuming you have some values of K1 and K2, which relate then how fast A is consumed to form B, how fast B is consumed to form C. Okay, now you take these two rates, K1 and K2, and you change their ratios. Okay, so in this first one, we could say the ratios were K1 and K2 were roughly the same. Because you see here, A is being formed, B is formed, and B is consumed. So the rate of decay of A is almost close to the rate of formation of C. So roughly K1 is equal to K2. But let's say K2 is smaller than K1. Okay, let's say K2 over K1 is 0.5. Okay, so K2 is 1 and K1 is 2, let's say, so the ratio is 0.5. Then what happens? Well, then A is consumed, B is formed, but it decays at a slower rate because the second reaction is slower than the first reaction. Now, what if K2 over K1 is? K2 is greater than K1. So it equals to 2. Now the second reaction is much faster than the first reaction. So B is formed and B is consumed. And similarly, you can keep going and you say K2 might be greater than K1 by 10 times. Then as soon as B is formed, it's consumed. So like this, based on different reactions and the relative rates, you'll have different behavior for the species profiles. And this is where we can start to make things like steady state approximations. So let's say now K2 and K1 are not equal. K2 is much faster than K1, way faster, like not 10 times, maybe 50 times or 100 times faster. Then, again, you have the same equations at play, but now because species B is consumed so much faster than it's produced, your curve might look like this. Again, A is consumed, B is formed, but it's consumed right away for a very large ratio of K2 to K1. Then we start to say that, okay, B is a transient species. It's as soon as it's produced, it's consumed. So then the rate of change of species B as a function of time is 0. Okay, the concentration is not 0. The rate of change of the concentration as a function of time is 0. We call that a steady state approximation. So we say this species B, the rate of change of the species is at steady state. So plus K1A minus K2B is roughly equal to 0. It's not true, it's not a fact, it's just an approximation that we use, which will help us to simplify the system because of the ratios of K2 versus K1. And then dC by dt, the formation of C, is still equal to K2 times the concentration of B. Now, if we make this steady state approximation, we can simplify how we make calculations. So now, again, species A is A naught times exponential minus KT. But now, because species B is at steady state, you can take this equation, K1A then has to equal K2B. So then K1 over K2 times concentration of A, or K1 over K2 times A naught exponential minus KT, gives us the concentration of B at steady state. And then again, we can link concentration of C directly back to A, because B was at steady state. Yeah? So now concentration of C is simply A naught times 1 minus exponential minus KT. Now, where does all this make sense in our practical system? So what types of species do you think are typically at steady state in a combustion system? Yes? Radicals. So let's say, again, here we had CH4 plus O2 goes to form, well, let's not look at CH4. Let's look at a different example. I'll put ethane up here. From now on, I won't even write arrows. I'll write just equal sign, because chemical reactions are just simply equations, okay? And we said this is going to form abstraction, so C2H5 plus HO2, two radicals, yeah? And let's say C2H5 so this is a radical, this is a radical, this is a radical, this is a radical. So let's say C2H6 plus O2 goes to form two radicals, C2H5 plus HO2. C2H5 then can decompose to form ethylene and hydrogen radical, okay? And then, well, many things can happen from there, many other different types of reactions. This reaction is the decomposition of a radical, okay? This will have a this is like a barrierless reaction almost, very low barrier of energy required for a radical to decompose because it's so unstable. So here K2 is maybe 1,000 times larger than K1, if this is 1 and 2. So then the species B, the radicals, are essentially at steady state. We can use a steady state approximation to determine, and then you can say the concentration of ethylene can be directly related to the concentration of ethane, yeah? And then, of course, you still have to consider the ratio of these chemical reactions, K1 and K2, to determine that concentration of ethylene. Okay, and we will use these tricks in the beginning tomorrow to show how we can find a set of chemical reactions that are relevant. But, of course, when we're doing computer simulations, we don't bother, right? We don't need to make steady state approximations anymore because our computers can calculate all these things super fast. But when chemists were trying to discover all these mechanisms by hand, like Hinshelwood did 100 years ago, he had to make all these approximations to simplify the set of algebraic equations and compare them against experiments. Today we can write all these algebraic equations down and solve them. We can write the differential equations down and solve them very quickly in a computer. Now, one thing we should note, though, is whenever we make these types of systems, because of the huge change in timescales for example, here, some species are, like species A is consumed over, let's just say this is milliseconds. Yeah, it's all consumed over 3 milliseconds. But species B is produced and consumed in a matter of microseconds. This is a huge difference in timescales. And in any type of system where you have a system of ordinary differential equations with widely differing timescales, you have a system of, we have what we call stiffness, okay? There's a system of differential equations where there's a big ratio between the maximum and the minimum timescale leads to the process of stiffness. And then your computer has a problem calculating all the different change in concentrations of species because the timescales involved are so big. Either it fails or it starts to just take a super long time, or it can even produce wrong information, a wrong calculation. In order to get the right calculation, you need to make the tolerances extremely tight, and then it becomes very computationally expensive to do it. So whenever we make chemical kinetic models, we have to be mindful that you might be producing a model with hugely different timescales, and if you feed this into an ordinary differential equation solver, you might crash the solver. Nowadays, we have things like Chemkin and Cantera, where the solvers are very robust. And they're able to, first of all, what they do is they're able to identify these stiffnesses, and then they make modifications to the tolerance limits so they can solve the system of ordinary differential equations. But oftentimes, again, it can add computational cost. So if you want to deal with this, you can still, people today do model reduction, and they take all these radical equations of species that are in a quasi-steady state, and they write them as these types of differential equations, or the concentration of B is just related to some rate constants related to concentration of A. And they don't bother solving a differential equation for this species. And that helps to simplify, again, the system of equations that have to be solved. So there's groups like Professor Tianfeng Liu at University of Connecticut, Dimitri Goussis in Khalifa in Athens. They do a lot of these. They make models highly simplified so that you can then put it into a more robust solver, or you can put it into a CFD simulation. And again, but tomorrow we're going to look more at all these steady state approximations because we're going to show how the early chemists used these approximations to discover the reaction mechanisms that were happening. Okay, and finally, we'll just wrap up to say, okay, what are we going to, when we talk about elementary reactions, we apply this concept of microscopic reversibility. This is saying that if you have a reaction in the forward direction, the reverse reaction follows the same potential energy surface. So that chart I showed before, we had reactants going to a transition state and down to products. The reverse reaction follows the same path, okay? That's a principle of microscopic reversibility. And if that's true, then we can say the equilibrium constant is related to Kf over Ki. I believe I already showed this before. So yeah, the forward rate over the reverse rate gives us the equilibrium constant. So then this equilibrium constant can be used to, if you have the forward rate, we can get the reverse rate by Kf over equilibrium constant of the reaction. And in terms of pressure, it's just related to the gas law. So Kp, our equilibrium constant of pressure, is then divided by RT raised to the stoichiometric coefficient of the reactant species. And as we said before, K is related to the change in Gibbs free energy of reaction, so exponential delta S over R minus delta H over RT. And we had these things before describing H and S. So we will use this principle of microscopic reversibility in our kinetic models, because for every reaction we will prescribe forward rates, we will prescribe thermochemistry properties, and the solver will automatically get then the equilibrium constants and get the reverse rates at each temperature condition correspondingly. Yeah, keep in mind this principle of microscopic reversibility is only true for, again, elementary reaction. So again, for this reactions of CH4 plus O2 going to CO2 plus water, it does not apply. The forward rate constant and the reverse rate constant are not related to the equilibrium because they're not even along the same potential energy surface. But for other reactions, yeah, when you're on the same potential energy surface, like one elementary reaction, you can relate the forward and reverse rate constants with the thermochemistry of the system. Okay, so that's it for today. Tomorrow what we're going to do, we're going to look back in the history how these guys like Semenov and Hinshelwood and others came up with these ideas. How do they know that I need to write down hundreds of reactions to describe one simple system like combustion? And then, of course, we'll talk about explosions, how explosions led to the formation of the first chemical reaction mechanisms. All right, so see you then, and have a good day.